You don't have to be a genius or a rocket scientist to realize that the universe is complex. You look out the window, you see trees and plants, birds, human beings, cars, buildings. You look up in the sky, you see clouds and weather, and then beyond that, planets and stars and galaxy. The universe is full of tremendous diversity and complexity. Now, why is this? Well, actually, the answer is quite mysterious, because really nobody knows. And in fact, there's something really quite bizarre about the complexity of the universe, because one thing we do know about the universe is the origins of the universe itself. So we know that the universe, the part that we see, began 13.76 billion years ago in a gigantic explosion that took place everywhere simultaneously, called the Big Bang. And then, expanded rapidly and cooled down, and then matter and energy started to clump together to form galaxies and stars and planets, etc. But the very first part of the universe was extremely simple. The universe was very, very uniform. It was almost exactly the same everywhere. Moreover, the laws of physics themselves are extremely simple. So how can you take something that starts off in a very simple state and that evolves according to very simple laws and gives you something that's highly complex, that gives you the complex universe we see today? Well, the real answer is nobody really knows. But I'm now going to describe a set of mathematical and physical results which gives us a really good indication of how and why complexity evolved. So let's just go through this process of complexity evolving and see if we can't, by teasing out what happened at each point, figure out general features of how complexity evolved. Okay, universe, very hot, featureless, expanding, starts to clump together, becomes less homogeneous, less regular. So there's something about the laws of physics that takes something that's regular and makes it more clumpy, more random looking, more detailed. Now, this is actually very strange by the ordinary laws of physics. But where does that come from? It comes from a special feature about gravity and the laws of gravitation. In ordinary stuff, like a cup of coffee, if it's at a particular temperature, it's all just homogeneous. It will stay at that temperature, gradually cooling down, remaining roughly the same temperature. It will remain homogeneous. But if you take gravity in the system, so you imagine the kind of cosmic cup of coffee as the universe itself spinning around, then gravity doesn't actually like things to be homogeneous. That's not the state of equilibrium where everything's in a nice balance. In fact, gravity likes things to be clumped up and non-homogeneous. So, in fact, gravity is famously, it has several features. One, gravity sucks, as my students are fond of saying. But another feature of gravity is that it's chaotic, which means a little tiny difference now can turn into a big difference later. So, for instance, a tiny little fluctuation in the density of energy in the very early universe can turn into the seed for the clustering of the matter that's going to form a galaxy later on. And where that galaxy appears is completely random. But the fact that the galaxy appears is not. So that's one clue. We need a system that has this feature that small differences now can make a huge difference later, the so-called butterfly effect, where a butterfly that flaps its wings in the Caribbean right now will give rise to a hurricane sometime later on in the summer. But we need more than that, because chaos on its own, sensitive dependence on initial conditions, is not enough. We also need the capacity to generate structures that have arbitrary intricacy. So here, what we need is basically some kind of dynamics which is guaranteed to produce complexity, not just randomness. Now here, if we look later on in the history of the universe, we see, aha, okay, how does this happen? So, okay, galaxies form in clusters, then smaller overdensities make stars, and then there are clumps that make planets around them. They're rotating around the stars. Then, some billions of years ago, something very remarkable happened. Life began. on Earth. Now, we don't know if or when it began elsewhere in the universe, but we know it began on Earth several billion years ago. Ironically, we know much less about the origins of life than we know about the origins of the universe. Universe, 13.76 billion years ago, Big Bang, temperature of billions of degrees. Life, we don't know. But we do know features of life now, and we can extract from these features of how complexity might evolve. Now, organisms have complex metabolisms that process energy, but at the basis of life is information processing. You have information in your DNA, and life consists largely of taking that information and expressing it to construct other cells, to carry out all the processes that happen at the microscopic level in living systems, to process information at the level of our brains so that we, can go gather food and, with any luck, get a date on Saturday nights, and thereby leading to the process of starting more life somewhere down the line, if we're lucky. So there's something about not just energetics and dynamics, but also about information processing. So let's turn to the theory of information processing. Now, we have a very good theory of information processing. It's called computation. A computer is a device that manipulates information. It takes information, divides it up into bits of information. So for instance, in DNA, you have 2 bits per base pair of DNA. And then on the function of what kind of bits you have, it flips those bits and processes information, flipping them in ways that are consistent with the program of the computer that's performing this processing. Now, we're accustomed to thinking of computers as being these complex electronic things like, MacBooks, iPhones, PCs, supercomputers, et cetera. Actually, basically anything right now has a computer in it. Your toaster probably has a computer in it. Trying to figure out, is a toast a little too dark? Oh no, quick, pop it up. But in essence, they're all performing this same bit flipping operation. However, there are levels of ability in processing information. So for instance, computers can be more or less powerful. So for instance, a thermostat that processes information in a very simple fashion just says, hey, it's got 1 bit of information. It's like, oh, do I need to turn on the furnace or not? Is it too hot? Not too hot? Okay, fine, we'll leave the furnace off. Or too cold? Oh, let's turn the furnace on. Too hot? Let's turn it off. So a thermostat is performing a simple information processing operation, but not as complex as the one that's going on in your iPhone or in your desktop. And there's a kind of threshold of computation. Once you pass over this threshold, which is called the ability to perform universal computation, then a universal computer can do any kind of information processing that we can actually conceive of. For instance, not only can a universal computer do things like, play Grand Theft Auto, locate you using your GPS, do word processing, number crunching, simulate the operations of DNA. At some point in the future, it might be able to simulate the workings of your brain. It might be able to simulate the future behavior of society. There doesn't seem to be anything that a universal computer can't do in principle. So what does a computer need in order to compute? Well, it needs bits, it needs energy to be able to perform the computation, and it needs a program. The program is a set of instruction that tells the computer what it should be doing. No, it's just, a program is itself just some sequence of bits. 0 means do this, 1 means do that, then the next 0 means do the other thing, and then 1 means now stop and give out the answer. A program is just a sequence of bits of information, but special bits that tell the computer what to do. Now, my claim is that by thinking about computation and programs, we can get to the essence of the origin of complexity in the universe. And this comes from a set of simple theorems which actually have their origin in the work of the famous Russian mathematician Kolmogorov around the 1960s. Kolmogorov was interested in trying to define how probability works. And to do this, he defined information in terms of computer programs. He said, oh, what's the information in an object? It's the length of the shortest program that will produce it. And then he also showed that very short programs can produce very complicated things. In fact, there's a very simple program for a universal computer that will by definition, produce all complex things. This program just says, well, let's look at all possible programs in order, and then let's evaluate what this one does, let's evaluate what this one does, let's evaluate what this one does, let's evaluate what this one does. Such a computer will systematically produce anything that could possibly be computed. And the program for doing this is very, very short. Sufficiently short, in fact, that you could hit upon it just at random by tossing bits out there at random. So now we have a theory that tells us mathematically what we need to get complex behavior. How does this work physically? So our mathematical theory says, oh, if you put random bits into a universal computer as a set of instructions or programs, this computer with high probability will produce any complex structure you can imagine. But what about the universe? The universe is not a computer, or is it? Actually, the dynamics of the universe support computation. We know because, hey, I have a computer, right? You know, the laws of physics support computation. And I know from my own research building quantum computers that the laws of physics support computation at the most microscopic and fundamental level, where elementary particles store bits of information, and every time two particles collide, those bits flip. So the universe is full of bits of information. Those bits are flipping. And in addition, you have random fluctuations that are being injected by quantum mechanics. At the Big Bang, it's like, oh, everything's like oozing around a bit. Here we get a slight overdensity of matter completely by chance. This slight overdensity is like a program. It's a program that says, later on, form a galaxy there. Then more complicated programs say, oh, here's a set of chemicals, start constructing membranes, which might then eventually have living stuff in it sooner or later. But the fact that the universe is constructing and evaluating programs doesn't require any specific mechanism. All it requires is the universe be a computer, be capable of computation, and that has random stuff injected into that. And that we understand. In fact, it happens all the time. And that's how, from extremely simple origins with very simple laws and just the injection of a few tiny bits of randomness in the history of the universe, we can get galaxies, stars, planets, people, computers, society, and the whole mess that we see out there.
In recent years, we humans have figured out a great deal about our universe. But that begs another question, which is very interesting and very controversial. Could there also be other universes? And do we have any evidence for this? Before we talk about other universes, parallel universes, let's remind ourselves what we mean by our universe first. Our universe does not mean everything that exists. It simply means the part of space from which light has had time to reach us so far during the 13.8 billion years since our Big Bang. So this is our universe. If space is bigger than that, then there are other universes, other regions of the same size farther away. If you want to know what's happening in the galaxy over here, you have to wait billions of years more for light to reach us. So we cannot see anything outside of our universe. One of the reasons this is so controversial is because many people say, oh, this is just stupid philosophical nonsense, you know. If we can never, by definition, see parallel universes, then it must mean it's not science. It's like talking about ghosts or something else that you can't see. But it's actually more interesting than this, because parallel universes are not a theory. They're a prediction from certain theories, which we can in turn test in various other ways. So to explain what I mean by this, let's look at another theory first. Einstein's theory of gravity, general relativity. It predicts a whole bunch of stuff which we can test and observe, like the motion of Mercury around the sun, the bending of light by stars, the time dilation that you can measure with your GPS and your phone, etc. And because of this, we take general relativity very seriously as a scientific theory, which means we have to take seriously everything it predicts, even things that it predicts that we cannot actually observe. Like what happens when you fall into a black hole. Einstein's theory of general relativity predicts exactly what happens inside black holes, but I cannot go observe it and then come and publish the results in a scientific journal here on Earth. It's impossible, right? But if one of my colleagues says, "Hey Max, I don't like black holes," they can't just opt out of black holes. It's predicted by the theory. If they want to get rid of the black holes, they actually have to invent a different theory of gravity, another mathematical theory that's different from Einstein's, which doesn't have black holes, but which can explain everything else that Einstein did. And that has proven very hard, so hard that after 100 years or so of trying, many of the smartest people on the planet have failed to do that. The point here is that for a theory to be scientific, you don't have to be able to observe everything it predicts. You just have to be able to observe at least one thing that it predicts. And if that convinces you to believe in the theory, you have to also take seriously the other stuff it says. Now, what does this have to do with parallel universes? Well, first of all, we have a different theory, the theory of inflation in cosmology. It's also a scientific theory. It predicts a whole bunch of things we have tested and observed very carefully in the cosmic microwave background radiation and three-dimensional galaxy maps. It's right now the most popular theory in my field for what put the bang into our Big Bang. It was pioneered by Alan Guth and Andre Linde and others. It's a beautiful mathematical theory. And it also predicts parallel universes. In particular, it predicts that space itself isn't just really big, but that the space is actually bigger than our universe, maybe even infinitely big. So the logic is that if inflation theory is correct, and we take it seriously, we have to take seriously the idea that space is bigger than our universe, that there are parallel universes, other regions of space that are just too far away for us to see. I call these parallel universes the level 1 parallel universes because they're not that different from our universe. The only difference is that over there, the particles started out in different places, so the galaxies formed in different ways. And if there are people over there, they will still learn the same things in physics class, but they might learn different things in history class because things started out differently and history unfolded differently. A fascinating thing about parallel universes is that the most interesting question now really to me isn't whether there are any, but how many different kinds there are. This is the least controversial kind, the first level. Then there's level 2. And that's something that you end up with if you combine the theory of inflation with one more idea. If it turns out that string theory or loop quantum gravity or whatever the ultimate correct theory is going to be that unifies all of physics, if it turns out that that theory has more than one solution with a homogeneous space in it, kind of like the equations for water have 3 different solutions, liquid water, ice, and steam, then this theory of inflation actually will create not just a big space, but it'll create a big space with each of these solutions actually happening. So the theory of inflation actually converts potentiality into reality. It'll make a universe with this kind of space, with that kind of space, with a third kind of space. Some string theorists think that there's 10 to the power 500 different kinds of space even. And what does it feel like to live in one of those parallel universes if they exist? Well, more interesting and diverse than in the level 1 kind, because they wouldn't only learn different things in history class, they would actually learn different things in physics class. They might learn, for example, that there are not 6 kinds of quarks, which is what I learned in physics class, but that there are 10 kinds of quarks, or 2 kinds of quarks. Many of the properties that we thought were fundamental properties of physics, according to string theory, are just telling you which particular solution of string theory you're in. Do these exist? We don't know, of course. How can we test it? Well, by testing inflation more and by studying string theory more to see if it seems to make any sense or not. If it does make sense, though, it actually would help answer another big mystery we have in physics, which is when you look around us in the world, our universe has all these numbers built into it that we call constants of physics. For example, there's a number that tells us how much dark energy there is. The value of the number is about 10 to the power minus 123. 0.000 blah, 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 1 with 123 zeros. And if you imagine that you could make your own universe and you could have a little dial, a little knob that could change each of these numbers, I would recommend don't touch those knobs, because it turns out almost anything you change by a little bit will kill all life. if you put in more dark energy than we have by a lot, you destroy all the galaxies. Dark energy prevents them from forming, for example. If you change another number to do with the Higgs particle, suddenly you can't have any atoms. And this is a deep mystery in physics. Why is it that our universe has these numbers which seem to be fine-tuned for life? Is this just luck? Or is it some kind of miracle, or what? Well, the level 2 parallel universes actually give a scientific explanation for this. Steven Weinberg made a famous argument many years ago where he said that suppose the level 2 multiverse exists and the amount of dark energy is different in different parts of space. Then you predict something like the Sahara Desert. Most of it is dead, no life, no galaxies. But there will be still, some places where it just where the dark energy has exactly the right value to allow galaxies. And that's, of course, where we should expect to find ourselves. If I know that I'm a Bedouin and I live in the Sahara Desert, I'm not going to be surprised to know that I live in an oasis. That's the only places there are people really living. And it paints this picture where the same thing is happening on a larger scale in our cosmos. After this prediction was made, dark energy was discovered, and a Nobel Prize was given for it. And this has made people take this idea quite a bit more seriously. It's still fair to say that it's very controversial. We don't know, but it's certainly a scientific question we can discuss, whether our reality is this big. We should also be mindful that we humans have again and again made this mistake of underestimating the size of our cosmos. First we thought Earth was the center of everything, right? Then we discovered that our solar system existed in a galaxy and a universe. So it might very well happen again. There's no guarantee in the laws of physics that we humans should be able to see everything that exists. And if we cannot, by definition, there are parallel universes. Well, and there's even more. There's a third kind of parallel universes which have come into the scientific discussion from studying not the biggest things, but from studying the smallest things, by studying quantum mechanics, the rules that govern how atoms and elementary particles behave. This is arguably the most successful theory in all of science. It's given us transistors, computers, cell phones, lasers, etc. But at the cost of some weird ideas. Quantum mechanics tells us that little particles can be in several places at once. If the particles can be in several places at once, well, I'm made of these particles. I should be able to be in several places at once as well. And in 1957, a young graduate student named Hugh Everett worked this out really carefully and argued that what it really means is that there is a third kind of parallel universes, where when you make certain decisions, effectively our world splits into several parallel tracks. If I get a parking ticket, there's a parallel universe maybe where I didn't. But there's another parallel universe maybe where my car was stolen instead. So you win some, you lose some. This sounds very philosophical, but it's the way to test this, again, is not by speculating, but by studying quantum mechanics more. In particular, we should try to build quantum computers, which is a kind of machine which takes advantage of parallel computation and effectively using these parallel worlds. If we try to build them, and there are millions and millions of dollars spent right now to try to do so, if it fails, because we notice that the basic equation of quantum mechanics is wrong, then we can forget about all these parallel universes. But if they succeed, and they can calculate something in 5 minutes that would take longer than the age of our universe to do on a normal computer, I think that will make many scientists take these parallel universes more seriously.
Quantum mechanics is by now a well-established branch of science. It describes the laws of our world at a kind of microscopic length scales. And it has been developed at the turn of the 20th century and applied to a wide variety of physical systems. By now, I would say the application, the use of quantum mechanics to describe the properties of the micro world is well established. while scientists still try to push the frontiers of understanding of subatomic particles and uncover kind of new underlying laws of physics, I would say that in terms of, for example, understanding of matter at the atomic scale, the job is mostly done. So what scientists and engineers are now trying to do is to take advantage of this knowledge and not only kind of describe and understand the matter of an atomic scale, but also try to control, engineer, and apply it to basically realize new devices and new applications. One of the fundamental principles of quantum mechanics, which is a key to many of those applications, is a superposition principle. So in quantum mechanics, one particle can be in superposition of two states at the same time. So in simple words, it can be at two places at the same time. So in principle, the object, the big microscopic object, such as, for example, a table, can also be at two places at the same time. It can be in superposition, as scientists say, in a coherent superposition of two states at the same time. So the state of this kind is not prohibited by the laws of quantum mechanics. And while for the small-scale systems, like, for example, a single electron, this existence of these superpositions have been established in many experiments. For macroscopic objects, of course, the superpositions do not exist in a real life world. So the reason for that is because these superpositions of this kind of macroscopic superposition states of the kind that I just described are extremely fragile. Anything which basically can disturb, or if you want to measure the position of such a superposition, immediately collapses the state, or basically it forces the system to be in one state or another. And this superposition principle is the basis for the new extremely active field of quantum science and engineering, where scientists are trying to implement, realize experimentally these quantum superpositions on larger and larger scale, and not only to experiment with such systems, but also to use them for different applications. So the kinds of applications that people are exploring form a very diverse set. One most known example is, of course, a quantum computer. So a quantum computer can be potentially extremely powerful because you can encode a lot of information in this kind of superposition state. You can basically create the state of a quantum computer which encodes multiple bits of classical information at once. So needless to say, this state it can be very interesting from the point of view of scientists, because it basically represents a new state of matter. But at the same time, potentially there are several examples of specific algorithms where quantum computer can outperform basically any existing or any conceivable classical computer possible. Quantum computer, in particular at this large scale, is very difficult to implement, and the reason why this is the case is precisely the reason why we don't see in everyday life this kind of superpositions of, for example, tables sitting in different rooms at the same time. However, even smaller scale quantum computers could be used for interesting applications. So one example of such an application is the so-called quantum network or quantum internet. So what you can do is basically use relatively small-scale quantum computers to, for example, enable the nodes of this network to communicate each other in a very fast and also very secure kind of fashion. So you can basically, use the laws of quantum mechanics to enable secure transmission of information. The reason why this security can take place can be traced back to the point of view that if you have a superposition, then any kind of perturbation, any attempt to measure it will immediately collapse it. So if anyone is trying to basically interfere with the secure network, this interference can be immediately detected. Another important direction is related to realization of new and understanding of new quantum materials. So as already remarked that when quantum computer performs its operation, in the process of its computation, it creates the states of matter which are extremely unique and unusual. So one can take advantage of these kind of properties to basically design the new types of quantum materials and quantum matter with the properties which do not exist in natural world. These states are extremely interesting and it's actually extremely challenging to understand and quantify it because they're very unusual. They contain the correlations which are very difficult to measure using conventional techniques. So this kind of work which is taking place in this field might enable us to gain unique insights into properties of this kind of materials and perhaps design new practical materials such as, for instance, high temperature superconductors which can conduct electricity without losses even under ambient conditions at room temperature. One final example that I would like to give is the work involving quantum sensors. As I already mentioned, these quantum superpositions, the underlying principle of quantum mechanics, are extremely fragile. And of course, this fragility is a main challenge for realization of quantum computers, but you can turn the tables around and ask a question whether you can use the sensitivity of quantum superpositions to the external perturbation to design novel kind of sensing or imaging techniques. So it turns out that such sensors can indeed be developed and realized. Some of these kind of sensors are already around, so the world's best atomic clocks are in fact making use of such superpositions, but it turns out that the family of these kind of sensors can be extended significantly, going all the way down to the novel techniques for example, biological imaging or imaging of living systems at the cellular or subcellular level. So this is the kind of work which is now going on in this field. This is an extremely exciting field, and some applications might be around the corner. So among the most significant intellectual challenges in these fields is a question of how big can be the system size such that the laws of quantum mechanics would still apply. You can formulate this question in different ways. For example, you could ask, so given that we have a given size of the system, for example, a quantum computer, how long can it maintain its quantum mechanical coherent state? Or alternatively, you can ask it differently and ask, for example, if you have a quantum material, at what length scale or at what temperatures can this material still feature quantum correlations? So these kind of questions are very interesting and very fundamental to the science of what we are trying to explore, but also they have some practical relevance. They are important for some specific applications. One last thing that I would like to mention is what I would say the application question or application challenge. That is, given that we now have in a lab some relatively small scale quantum systems, or if you want, small scale quantum computers, which we can control, manipulate, and measure, can this small scale system enable new capabilities, both in science and also in terms of applications in the real world? So this is also another important question.
Quantum simulation means that we simulate the behavior of one quantum system with another quantum system. In other words, if there is one quantum system which is maybe complicated to prepare, or certain things happen on a microscopic scale, if I can create another quantum system where on a whole different scale the same equations apply, then the same equations have the same solution. That means this system behaves like the other system, and I can study the first system by deeply analyzing the second system. So this is meant by quantum simulation. Create a system, a quantum system, which has the same properties as the system you're interested in, but which is easier to manipulate and easier to study. So that means that within the field of ultracold atoms, that we use ultracold atoms to recreate a quantum system which has interesting properties. And you can say it started early on. The Bose-Einstein condensate is a superfluid gas. And as such, you can regard it as a quantum simulator for superfluid liquid helium. Superfluid liquid helium is much more complicated, but some aspects of superfluid helium, especially the equations for superfluidity, are similar or are the same as we can implement with the Bose-Einstein condensate. So often when we say quantum simulation, we don't want to quantum simulate the messy part of the system we are interested in. We want to build an idealized, simplified model. And Bose-Einstein condensation is the most pristine, the most simplified model of superfluid liquid helium. When we took fermionic atoms and paired them up and studied the superfluid character, we had done a quantum simulator of superconductivity. We realized the simplest system which was described by the so-called BCS, Bardeen-Cooper-Schrieffer theory for superconductivity, which is used to describe many superconductors. But we had sort of taken it in its pure form. We didn't have a lot of other complications. We had just directly built, stripped it to the bare bones and built an idealized BCS superfluid. And this idea of simulating a quantum system with ultracold atoms is now the goal for many, many research groups. Just to give you other examples, we are interested in magnetic behavior, ferromagnetic, antiferromagnetic ordering. And we want to use our atomic Legos to arrange atoms in a periodic lattice and look for ordering, that the spins of the atoms are either parallel or anti-parallel, there will be phase transitions and such. So we want to use ultracold atoms as a toolbox, like a box of Legos, and quantum simulate in its purest form magnetic behavior which is not yet fully understood. Just to give you two other directions, one of the biggest discovery in condensed matter physics have been topological insulators and Majorana fermions. We hope that very soon we are able to quantum simulate those materials, in other words, recreate those materials with ultracold atoms. But then we have a system where we can change parameters, we can use very different forms of study, we can look at the system sometimes atom by atom and gain much more insight into these two new classes of material. Or to give you a final example, in one of my labs we've we've started to study what would happen to electrons in very high magnetic fields. And I'm talking about magnetic fields which are 10 or 100 times stronger than the strongest magnets on Earth. So we want to understand what would happen to electrons in such magnetic fields which cannot yet be produced because of technical limitations. So what we are doing is we are using ultra-cold atoms, and then we are shining laser light on them, and the laser light makes the atoms move around exactly in the same way as electrons move in a strong magnetic field. So using laser light, we are implementing the equations of motion for electrons in high magnetic field. So now we have a system of ultra-cold atoms which behaves in the same way as electrons in magnetic fields which cannot be realized in the laboratory. So now we have a quantum simulator which is actually simulating a form of matter which does not yet exist on Earth because we don't have the magnetic fields to produce them. So this is how we want to sort of move the boundaries of our understanding of materials and figure out what is in principle possible in nature, even if it cannot yet be technically realized. So this gives you sort of some ideas what quantum simulators can do for us. But I should actually sometimes say that when I create a Bose-Einstein condensate, I feel I've created a new superfluid and not just simulated a superfluid which has maybe already existed. So the two aspects of creating a new system with ultra-cold atoms or emphasizing analogies to other systems, which would be called quantum simulation, go hand in hand. The concept of quantum simulation can be traced back to Richard Feynman, who said in the 80s that it would be very powerful if he could create a quantum system which would be analogous to another quantum system, and thus we would have quantum simulator. I mean, this was an idea which people had in their mind, but there was major new interest in this idea in the context of quantum computation. In a way, a quantum computer is a quantum system which can be programmed to simulate any form of matter you can think of, because you can program your quantum behavior, you can program your quantum computer. However, we do not yet have, and probably we won't have it for a long time, a general purpose quantum computer. So what we do with ultra-cold atoms can be regarded as a special purpose quantum computer which cannot be freely programmed, but by choosing the kind of atoms and the interactions and forces between the atoms, we have now a quantum simulator, some people would say an analog quantum computer for a special purpose, namely solving the equations which describe certain forms of matter. The major challenge in quantum simulation is to do the simulation right. We have to control every single aspect, and so for quantum simulation we often need, need a perfect system. We have to perfectly prepare. Sometimes we try to do a quantum simulation, we arrange laser beams and atoms, and what happens is, puff, the atoms just heat up. And then we are back to the drawing board. We have to figure out what is responsible for the heating. Sometimes it's just technical noise, but sometimes it's something fundamental we have to understand. So we are at the frontier of knowledge, we are at the frontier of science, and almost by default everything we try first doesn't work, and we have to figure out how to make it work. So it's ultimately moving the barrier, is moving the frontier of knowledge, and doing more and more sophisticated quantum simulation is an endeavor where we have to learn to master technology, but also where we have to develop a deeper understanding of ultra-cold atoms and how they interact, for instance, with laser light, and then we can use it to our advantage and quantum simulate new materials. What would be the steps from a quantum simulator to a quantum computer? Well, first, quantum computer and quantum simulators have a lot in common. They require control over quantum systems. They require that we keep the system cold, we keep it in a pure quantum state, so we don't like heating and dissipation. But quantum simulators are at this stage easier to realize in quantum computers because we can put many atoms together, they interact, and that's how they perform the quantum simulation. In a general purpose quantum computer, you want to be able to control, or so to speak, to program each individual atom. So you may need a way to have sharply focused laser beams which can, so to speak, tell each atom what to do and such. So there are many more complications and technical steps until you can have a general purpose quantum computer. So currently there are dozens of research groups who pursue quantum simulation with ultracold atoms. Quantum computation is even a bigger field. There are hundreds, if not thousands, of research groups who pursue quantum computation with all sorts of different systems, solid-state systems. People use ion traps, and people use neutral atoms. So the field of quantum computation covers a wide area of methods, and people don't know yet which system will be the easiest to realize a quantum computer, because nobody can predict with which system it will be easiest to overcome the outstanding problems. So what is the difference between quantum simulation and quantum computation? Well, I mentioned they have something in common, but there are also differences. In quantum computation, you have, for instance, several ions, and each ion forms a qubit. And in order to perform a quantum computation, you have to control the quantum state of each individual part of your quantum computer. Each qubit you want to program, and you want each qubit to perform in a programmable way quantum operations. In a quantum simulation, this is not necessary. We just throw many atoms, you can call them qubits, together, but then they interact with each other through their natural forces. So in other words, in a quantum simulator, we pick the atoms in such a way that they interact with each other the way we want them to interact without individually programming it. So you can say it's maybe more the top-down approach, that we use many atoms and we make sure they interact and do their thing. In the quantum computer is more bottom-up approach. You take atom by atom, you program each atom to do what you want to do, and then with the quantum algorithm you get those atoms to perform the quantum computation you want them to do. So currently quantum computation, this approach of programming each atom, is limited to, I forgot what currently the record is, to about, let's say, 20 ions, 20 qubits. Whereas quantum simulations with neutral atoms are often done with 10,000 or a million atoms, because we do not have to program them atom by atom. But I expect that in the future, the two areas of quantum computation and quantum simulation will actually grow together. And ultimately, one vision which myself and my colleagues here in the Center for Ultracold Atoms pursue is that the top-down and the bottom-up approach may actually meet in the middle.
A quantum computer is a device that stores and processes information at the level of individual atoms and elementary particles. Now, quantum computation has two parts. First of all, it's quantum mechanical, and secondly, it's a computation. Though quantum mechanics sounds a bit strange, and quantum mechanics is weird, technically speaking, in some sense, the quantum part is easier to understand. Quantum mechanics is just the theory of physics that explains how things behave at their smallest and most fundamental level. So it's the branch of physics that governs how atoms, photons, particles of light, electrons, elementary particles behave. So if we're going to build a computer at the scale of atoms and elementary particles, by its very nature, it will use the laws of quantum mechanics to function. And we'll see that the weirdness of quantum mechanics, the fact that quantum mechanics is strange and counterintuitive, actually helps to allow us to do computations in ways that you couldn't possibly do with a laptop or an iPhone. So the second part about quantum computation is computation. So what's a computer? Actually, in some sense, this is a little harder question. I mean, I know a computer when I see one, I like type on one, I like make phone calls on one, I use like Google Maps on a computer. But in fact, the idea of computation is a deeper and more general one than just whether you happen to have like an Apple or a PC or an iPhone or a Samsung. It's the notion of processing information. So what a computer does, a digital computer takes information and breaks it up into the smallest possible chunks of information, which are called bits. So a bit is an elementary distinction between two possibilities: yes or no, true or false, 0 or 1, or for that matter, inside a computer, capacitor at its low energy state or capacitor at its high energy state. And that's in fact how bits are physically stored inside an ordinary digital computer. Low energy is 0, high energy is 1. And then to perform a computation, the computer, having broken up information to its smallest chunks, it flips and manipulates those chunks and bashes them into them and transforms them in very general ways. In fact, there's a notion called universal digital computation that says what is the most powerful thing that a classical computer can do by taking bits and by flipping them in a systematic fashion. So a quantum computer is a computer that takes bits and manipulates them in a systematic fashion, but also operates at the level of atoms, elementary particles, photons, particles of light, electrons, where the laws of quantum mechanics hold sway. Quantum mechanics is weird. This is a technical term, weird. Niels Bohr, one of the inventors of quantum mechanics, said, anybody who thinks they can understand quantum mechanics without getting dizzy hasn't properly understood it. Actually, he said it in Danish, which was more impressive. But it's true that quantum mechanics is strange and counterintuitive. To get a feeling of this essence of this quantum weirdness, think of something called wave-particle duality. I know it sounds weird. Woo, wave-particle duality. What does that mean? Well, it means that things that we think of as particles, like atoms or electrons, have waves that are associated with it. Similarly, things that we think of as waves, like light or sound, have particles that are associated with them. This all takes place at the very microscopic level. Now, what this means is that when you store a bit of information on a quantum computer, say on the position of an electron, that this electron has a wave associated with it. So in a classical computer, the way you could store a bit is, well, okay, 0 is low energy state, a whole bunch of electrons over here. 1 is a high energy state, a whole bunch of electrons over here. Now let's miniaturize this until we have a quantum bit, which is a single electron. So 0 is a single electron over here. 1 is a single electron over there. Well, that's fine. You know, electron over here is 0. You move it over there, it flips to 1. You move it over here, it flips back to 0. You have 2 electrons, you move them back and forth, you're flipping multiple bits. So there's nothing wrong with storing and processing information at the level of single electrons. The problem is that the electron is a quantum mechanical thing. And even though it's a particle, it has a wave that's associated with the electron. The wave that's associated with an electron has something to do with where the electron is. So if the wave for the electron is all over here, then the electron is over here and it's 0. If the wave for the electron is all over here, then the electron is over here and it's 1. But the funky thing about quantum mechanics is that the waves don't have to be just here and there. You know, it doesn't have to be either here or there. A wave is an extended object. You can have a wave that's here and there at the same time. Well, what does it mean to have a wave for an electron that's here and there at the same time? It means that this one electron is simultaneously here and there at the same time. So a quantum bit, or qubit as it's sometimes called, has a funny feature that it can be both 0 and 1 simultaneously, because this electron is here and there at once. Now, this is just weird and counterintuitive. There's no classical intuition that corresponds to having something like, you know, a soccer ball being here and there simultaneously, even if Messi can make it look like that every now and then. So with an electron, you really have electron here and there at once. So a quantum bit or qubit can be 0 and 1 at the same time. So the central feature of quantum weirdness, this wave-particle duality, which is strange and counterintuitive and hard to grasp with our ordinary intuitions, this means that quantum bits can be 0 and 1 at the same time, and that means that quantum computers can perform computations in ways that classical computers can't. A nice way of thinking of this is if a classical computation is a sequence of bit flips for multiple bits, flipping back and forth multiple times, you can think of this in wave terms. You can think of this wave for this as just being a single wave, like a single pitch, like ah, or like a single chant, like ah, 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 ah. So a classical computation is just one wave, a series of pure tones. A quantum computation, by contrast, the waves for all the bits can have multiple values at once. So it's a symphony. I can't actually sing a symphony on my own, but you can imagine a symphony. And what's happening in a quantum computation is that the waves corresponding to each of the computations add up in a way that gives you interference and harmony between these different waves. So the possibilities that are available to a quantum computer are much greater than the possibilities available for a classical computer. In particular, let's think of what the purpose of bits are inside a computer. So if I have a 0 or a 1, a bit could be, could be data. It could mean 0 and 1 sounds so prosaic. Suppose that I ask my fiance, I ask my girlfriend, will you marry me, right? And she sends a bit of information with 0 for no and 1 for yes. Okay, this is a very important bit for me. Maybe she emails it to me. That's maybe not the nicest way to accept a marriage proposition. So for a quantum marriage, she could send a quantum superposition of 0 and 1 at the same time, meaning she's feeling ambivalent in a very quantum mechanical fashion. So what happens when I actually look at the answer to her question? Well, these quantum bits have the feature that if you have a bit that's 0 and 1, 0 no and 1 yes at the same time, and I actually look to see, okay, is the electron over here? No. Is the electron over here? Yes. Then half of the time I'll find the answer no, half of the time I'll find the answer yes. So if my girlfriend were to tell me this would be her way of essentially flipping a coin about whether she's going to marry me or not. Now, in a computer, a bit can just be a bit of data, like 0 or 1, but a bit can also be an instruction. So 0 could mean, do this, and 1 can mean do that. Like, to get away from marriage metaphors, they're making me uncomfortable. To get away from metaphors about marriage, let's go to mathematics. So 0 could tell the computer to add 2 plus 2. And 1 could be the instruction of the computer that says add 3 plus 1. In a classical computer, a bit can either be 0, add 2 plus 2, or 1, add 3 plus 1. But in a quantum computer, because a quantum bit can be 0 and 1 simultaneously, then if you take such a quantum bit and give it as an instruction to a quantum computer, the quantum computer will add 2 plus 2 and add 3 plus 1 at the same time, in some funny quantum sense. So these two different computations occurring at the same time are like two different voice parts in a chorus, or two different violin parts played simultaneously in a symphony. And the essence of the quantum computation comes from the interference between these different parts. Just as for us, if we hear two sounds played at the same time, it has a sound that comes not from just one sound on its own or the other sound on its own, but from the interference of the two sounds together. Now, this may sound kind of strange and esoteric, and indeed, when you build quantum computers, you're building computers where the components are at the level of individual atoms. They're very, very tiny computers. You want to keep track of them, because if you lose them, you're never going to find them again. We can ask what we can do with this, and why should we try to do this when we have perfectly good classical computers? Well, the idea of quantum computation, of storing bits on individual atoms, was proposed in the early 1980s by Paul Benioff at Argonne National Laboratories, Richard Feynman at Caltech, and David Deutsch at Oxford in England. Quantum computers weren't built, the first prototype ones weren't built until the early 1990s, when I proposed how you could build a simple quantum computer. And indeed, Dave Wineland, the Nobel laureate in physics, received his Nobel Prize in part for building some of the first simple quantum computers. In 1994, however, a real impetus came for building quantum computers when Peter Shor, then at AT&T and now at MIT, showed that if you could build a quantum computer, even a small one with a few tens of thousands of quantum bits, able to perform 1 million operations, which is nothing for a classical computer. If you could get this quantum computer doing this symphonic kind of computation, then it would be able to break all the codes that we use to transmit information secretly over the internet. And as you can imagine, at that point, a bunch of people's ears perked up, not just individuals, but agencies who like to keep secrets and who like to find out other people's secrets, of course. So these agencies and lots of people said, oh, wow, it would be great if we could build a quantum computer. And so in the early mid-1990s, this entire field of quantum computation took off. I and my colleagues started building quantum computers. Everybody around the world, well, not everybody, but hundreds of people around the world started building quantum computers. Now we have quantum computers which, even if they can't factor large numbers and break codes, a la Shor, they can still do all kinds of interesting things. We're using quantum computers here at MIT to investigate fundamental physical properties of matter. You can program a quantum computer to see what was happening in the universe at the very first instant of a second. You can use quantum computers to investigate weird and funky effects that go under names like entanglement, where particles of light know much more about each other than they have any right classically to do so. You can use quantum computation and quantum communication to transmit information in a provably secure fashion where the security is guaranteed by the laws of nature. And even if these aren't good enough reasons for doing quantum computation, there is another good reason, which is this tremendous fun. And I myself, from working on these quantum computers over the last 15 or 20 years, have had a fantastic time exploring how nature works at its smallest and most fundamental scales.
Among the two most fundamental challenges in the field of quantum science and engineering is the challenge of trying to maintain the coherence, or in other words, quantum mechanical behavior for the large-scale quantum systems, such as, for example, quantum computer, as well as what I referred earlier to application challenge. And the application challenge means is that by now we have in our laboratories the systems composed from several quantum bits. They can be viewed as a kind of small-scale quantum computers, and we gained quite a substantial degree of control over the systems, and we can measure and manipulate them very precisely. What we would like to do now is to look for applications of the systems. One of such applications naturally emerges due to fragility of the quantum states. So indeed, the quantum superposition states are very sensitive to external perturbations, and while this is the main problem for realization of quantum computers, this property makes it possible to utilize these quantum systems as sensors of external perturbations. Perhaps one of the most well-known examples of such an application is an atomic clock. So an atomic clock makes use of the superposition states of isolated atom to essentially define the standard of time, the second. Work on atomic clocks have been going over the past half of a century. In fact, it motivated the development of the entire field of quantum science and engineering. And by now, atomic clocks play a really important role in our society. For example, they enable things like global positioning system. At the same time, over the past decade or so, an intensive research have been carried out into identifying and studying new types of quantum bits. In other words, the new types of quantum systems which can be isolated, manipulated, and measured. So it turns out that some of those systems can be pretty robust, and indeed we can now implement small-scale quantum computers which are composed from several quantum bits inside the solid-state system, and we can control, manipulate, and measure them under ambient conditions at room temperature. Those type of systems can be extremely small. They can be nanometer in their size scale, which makes them quite unique candidates for the realization of new generation of nanoscale quantum sensors. The reason why this is the case is because if we can create the superposition of these states of those quantum systems and we can measure them, we can explore the sensitivity of these superpositions to external perturbations, such as due to the external electric fields, magnetic fields, or temperature, to measure these physical properties of surrounding objects. And we can do it now with very high sensitivity, but also on very small length scale, on length scales down to few nanometers, which is impossible with any other existing technologies. So the specific direction which my group is currently exploring involves the use of impurities in diamond, which behave like an isolated atom-like objects. So they essentially atomic scale, and they also have properties which are very similar to those of isolated atoms. So those isolated atoms, however, are sensitive to the surrounding environment, and in fact they can be explored to measure electromagnetic fields or to measure temperature. What makes them especially unique is that these impurities can be controlled under ambient room temperature conditions, and they can be integrated into the living objects. So as a result, we now have a new tool to explore biological systems at completely new scales, involving, for example, subcellular resolution. The kinds of applications that this technique might enable us to explore is actually wide-ranging, and I'll just give a few examples here. The first example is related to magnetic resonance imaging. So this is, of course, a fairly well-developed technique which is now used in medicine, and it is actually a unique tool, for example, which enables one to, study things like, brain and, basically diagnose some diseases in a very precise, non-invasive way. However, the conventional magnetic resonance imaging works only on length scales which are fairly large. So they are sort of the best resolution of this technique is about maybe 1/10 of the millimeter spatial resolution. By using those novel sensors which we are now developing, it is possible to extend these techniques to length scales which are at least factor of 1,000 or even more precise. Specifically, we could now explore the realization of the magnetic resonance imaging on very small objects, such as, for example, individual molecule. Another direction which is being explored involves the use of this quantum system to measure temperature at sub-micrometer length scales. The specific idea is that local temperature affects these quantum objects in such a way that we could basically read out the local temperature by using optical techniques, using laser light. This might also enable some pretty unique applications. For example, local heating is now explored as a cancer therapy to kill cancer cells in a very targeted way. By monitoring the temperature, it might be possible to dramatically improve the performance of this kind of methods. And these techniques can have a real-world, kind of relatively near-term applications. One final example that I'd like to give involves a grand challenge. It involves an application to the grand challenge in another domain of physics, which is a brain science. So brain science is by now a very active field where researchers are really trying to understand and unravel the ways how our brains work. One challenge there is to develop novel tools and techniques which might allow us to monitor the brain activity. By using the nanometer size quantum sensors, it might be possible to monitor the brain activity in some remarkable ways in real time and explore some unique applications involving, for example, the interface between brains and machines. Obviously, the performance of the sensors is a key factor in all of the applications which I have described. One of the questions which, in my view, is extremely intriguing is to what extent we can take advantage of techniques such as, for example, quantum entanglement, which basically is a correlations between different particles which you can create through quantum mechanical interactions to enhance the performance of the sensors. So this is a very fundamental question. Under idealized laboratory conditions, it is possible to create this kind of entangled state. And as a matter of fact, this is a key to the operation of the quantum computers, to the speed up that quantum computers enables us to do. And the question is, can we take advantage of this kind of quantum mechanical entanglement to improve the sensors operating under realistic laboratory conditions, perhaps even inside of the living objects, inside of the living cells? So this is one important question. Another important question is related to what I would say is a killer application of these ideas. And the fundamental question is whether this new generation of quantum sensors will enable us to really do biology or biomedicine at a fundamentally new level. Will it enable us to treat diseases at subcellular levels? Will it enable us to really understand how the brain works? These are all questions which we have to address and explore. They're all interdisciplinary questions. So where essentially quantum science and engineering brings up the tool, but of course this tool has to then sort of be coupled to the real systems, sometimes living systems, and to what extent can we really use this speed up, or additional sensitivity, which is provided to us by a quantum system, is something which we are still exploring.
Computers today, what we call classical computers, operate on the following principle, and that is that some transistor or some group of transistors act as what we call a bit. And so this bit can be 0 or 1. And the fact that this group of transistors can form what we call a gate, so an AND gate. That means we can process information. We can have 2 bits come in, say 0 or 1 on each one of these, and then information can come out either 0 or 1. And this forms the backbone of classical computation. Classical computation, as you know, eventually we add these things together and we can create objects that add numbers. They can get more and more complicated. In fact, inside your cell phone are billions and billions of transistors to create computation that allows you to connect to the web or do other things with computation. This idea of computation is very old. It works extremely well. And one of the reasons it works well is because each one of these groups of transistors kind of self-filters noise out. Now, there is an entirely different way of thinking about computation, and that is from a quantum mechanical perspective. Well, not classical anymore, but quantum mechanical. And it was shown fairly recently, about 15, 20 years ago, that there are certain kinds of problems that you can approach using a quantum computer that you can't approach using a classical computer. So there's, for example, trying to optimize a path that a traveling salesman takes, starting off in one city, and he has to visit many of these different cities until he gets to a final city. The question is, which path does he or she take, to minimize the amount of time that is spent on the trip? And that turns out to be a very hard problem. That computational complexity, the amount of time it takes to compute that, goes up very, very quickly given as a function of the number of cities involved. There are other problems that are like that. For example, the problem of factoring a number which is made up of 2 prime numbers. You may think, well, that's not a very interesting problem. Perhaps not inherently interesting, but from a practical perspective, in fact, the difficulty of that problem is what all private or encrypted communication relies on. And so trying to simply factor a number becomes very difficult as the length of the number becomes longer and longer. It becomes very difficult for a classical computer. For a quantum computer, it turns out those problems can be solved very, very quickly. So needless to say, if we had a quantum computer, it would really transform how we think about communication, how we think about computation. What is a quantum computer? There, the idea is not to have these groups of transistors, this kind of classical idea of transistors grouped together to form gates, but we actually have individual quantum objects. That is, if we take the simplest version of this, it's the spin of an electron. So the spin of an electron is a very simple, special quantum object. If I went to measure the direction that spin is pointing in, it turns out in the laboratory I only get one of 2 answers. I can either have spin up or spin down. And so we can think of that as being 0 or 1. If we wanted to map this idea over to classical computation, or at least our version of classical computation, we have what's called a quantum bit. It can be 0 or 1. But of course, that's not enough to do computation. In the classical picture, we had groups of transistors to form a gate, and then we hook these gates together to make something that eventually adds numbers and then ends up being in your cell phone. The question is, now we have these quantum bits. How do we connect these quantum bits together? And this has been a very challenging problem. And one of the areas of research which shows some promise for doing this, for coupling these bits together to actually form a computer, is ultracold molecules. What do ultracold molecules have to do with quantum bits? Well, it turns out a polar molecule looks very much like a spin. So a polar molecule might have an atom here, let's say sodium, and then the other atom here, chlorine, and that's what makes salt. And the molecule has an electric dipole moment that goes along this axis. So I can think of this salt molecule as being aligned this direction, or this direction. Here's 2 different molecules. They can be aligned like this, like this, like this, or like that. And That still isn't enough to do quantum computation, just the fact that those molecules are there. I have 2 bits, and now the question is, how do I couple those bits together? That turns out to be a very hard thing. But research is going in the following direction, where I can take these molecules and I simply put them next to each other, and that naturally couples them. The way that they're coupled is through the electric dipole moment. So here is an electric dipole, and it has an electric field, like so. Here's another electric dipole, it has an electric field. And these fields interact. And so that means there's an energy difference between this and this and this and that. So there's different energies involved. And so what it means is that if I have a certain quantum bit state on this molecule, it will affect this molecule because there'll be a small energy difference, and that means that the molecule will evolve. It will evolve and rotate around because of its proximity to this molecule. And that rotation will depend on whether this molecule is up or down. And that is a core coupling that allows you to make what's called a quantum gate. And you can take these molecules and arrange them in a way that you can form a quantum computer and address each one of these molecules with a laser. But how do you hold the molecules? We're used to thinking of molecules in a solid, and there the molecules are right next to each other, and they're in a particular arrangement, and it would take a very large large amount of energy to rotate this molecule around. So a solid doesn't work for us at all. What about if in a gas? If we took a gas of these molecules, then what would happen is they'd be running around and once in a while would bounce into each other. And that's a very non-controlled situation. Somehow we want to hold the molecules just right next to each other at a certain distance, and we want to hold lots of them. And we want these molecules to have the right properties to do quantum computation. There are a few other properties that you need to do quantum computation, and we need the specific molecules that have those properties. The way it turns out that it's possible to hold these molecules is that we can use light to hold the molecules. So if we focus light down, we can create little wells for the molecules. That is, the light will interact with the molecules, not with this electric dipole moment, but some other structure in the molecule. And the light will come in and interact with the molecule, and turns out we can focus the light in the right way that the molecule will sit there, will be trapped. But the interaction between the light and that molecule is very weak. And so we need to make the molecules ultra cold. We need to make them so cold that this very weak effect of the light holding the molecule is enough to keep it still. If I try this with room temperature molecules, then what happens is I focus the light and the molecule will just fly through the laser beam and be almost not affected at all. So we need to have ultra cold molecules, we need to have them the right molecules, and we need to have them the right distance apart. And so the question is, how do we make ultra cold molecules that are that cold? Well, there's lots of different ways that people are now looking to do that. One of the methods that we use, which contributes to a whole class of these cooling methods, is to cool the molecules by colliding the molecules with a very, very cold gas. So we take a very cold gas of helium, the helium gas collides with the molecule, and that brings it down to, well, it sounds cold, but it's 1 Kelvin. So 1 Kelvin is minus 273 degrees Celsius. So we get the molecules around that temperature, and now the question is, how do we get them colder than that? And the work that's being currently pursued is to laser cool them. We cool them to around 1 Kelvin by scattering with helium, and that works very well. And now a number of groups, including ours, is trying to create a gas of molecules that are in the microkelvin temperature range. And we do that by, instead of scattering helium, we scatter photons. We take a laser beam and shine a particular kind of laser light on the molecules. And the molecules will absorb the laser light and then re-emit the laser light. And that turns out to give the molecules a little kick. And we can arrange things so that kick is always in the direction opposite the way they're going. And this will lower their velocity, lower their kinetic energy, and cool the molecules. And there's good theory that describes that this should be possible. And there's some experiments done by Jun Ye at Jilla and Dave DeMille at Yale, which have shown that this can be done in one dimension. And now we want to do this in 3 dimensions to create a 3-dimensional cold gas. Once it's cold enough, we can then turn on our special other laser, which will hold the molecules in this arrangement. So the future of this is really quite broad. Once we overcome the technical difficulties of working with the molecules, we can use these molecules arranged in this particular way to do things that really are kind of almost science fiction, where we take this arrangement of molecules and we can do computations that, for instance, describe new materials. So we can put into our quantum computer, a special quantum computer that's called a quantum simulator, and try to devise ideas for new kinds of materials and use this quantum simulator to calculate what those properties of the materials might be. And we can tune parameters of the materials and figure out, oh, we should build a material like this, and then go into the lab and actually build a real material for using an aircraft or something of very important nature like that. And so the future is really an amazing horizon for these kinds of activities. So there's 2 unsolved questions here. One is technological, which is, can we take any molecule we want and cool it to these low temperatures and put it into a lattice? There are many technical challenges to that. The other is really unanswered, is once you have this quantum simulator, what kind of problems can you solve? We don't know yet. We, of course, have theory of some problems that you will be able to solve, but it may be there's a whole world of problems out there that we've not thought about. And so one of the fundamental intellectual questions here is what are going to be the limits of this kind of quantum simulation?
A laser is a device in which atoms or other entities radiate by stimulated emission into a single radiation field, which produces intense radiation in a single mode. An atom in a laser radiates by spontaneous emission. When it does that, it generates a photon. When the radiation from the laser is absorbed on a surface, for instance, the photons are destroyed. So the basic process of creating photons and destroying them is quite natural in light and part of the operation of a laser. Well, the idea of an atom laser seems absurd because you cannot make atoms and you can't destroy atoms either. So the title would seem to be a misnomer, but in fact it's quite accurate. The atom laser was a product of the discovery of Bose-Einstein condensation in 1995. That's Bose-Einstein condensation in atoms. In Bose-Einstein condensation, the atoms in a system, instead of being in many, many different quantum states, are all in one state, and that's the lowest energy state of the system. The system in this case is defined not by the walls of a box, but by magnetic fields or electrical or optical fields, which confine the atoms in space, but they are confined, and that their motions are quantized. Normally, the quantum numbers for these motions are tremendously high numbers, but in the Bose-Einstein condensation, the atoms are moving so slowly that the quantum numbers are small, and in fact, when the condensation takes place, the quantum number is 0. They're in the ground state of the system. They're standing still as well as the uncertainty principle allows. Now, these atoms are all in a single quantum state, just like the photons in a laser are all in a single quantum state. This means that there is a common wave function to all of the atoms. There's a common phase function which would describe all of the atoms. The atom laser was first demonstrated by taking these atoms in this ground state in experiments which were done here at MIT by Wolfgang Ketterle. and cutting the cloud of atoms in two, kind of with a laser knife. Okay? So now you have two clouds, but each of these clouds has a common phase factor. They're coherent with each other, and the clouds move together. So when they come together, if you take a picture of it, first you see these two halves, and then you see the halves moving together. But what you see are interference fringes. And these interference fringes are what you would expect for laser operation. It's because each half of these clouds has its own wave function, its own phase, and when they come together, the phases can add or they can subtract. It's really quite remarkable. It's as if I have a stream of atoms coming this way, and I look at them in front of me, and I see them, and I have a stream of atoms coming that way, and I look at them, and suddenly they've disappeared. Well, they haven't vanished, because if I find fewer atoms here, I find more atoms there, like in an interference pattern. You don't destroy light, but you redistribute it. Nonetheless, it's a demonstration of adding atoms to atoms and getting nothing. So it really was laser operation. This theme of the optics of atoms has developed remarkably in the years since then. Most of the things that you can do with light, you can now do with atoms. And actually, there are quite a few things that you can do with atoms that you can't do with light, because atoms are certainly not like photons. Photons are highly relativistic. They move at the speed of light. Atoms are ordinary matter, and they move at atomic speeds. But most interestingly, atoms interact with each other, and photons do not. The reason we have such beautiful optical phenomena is that classical optics is intrinsically linear. Maxwell's equations are linear equations. If you have a stream of atoms together described by a simple wave function, the wave function is intrinsically nonlinear, and the atoms can interact with each other, and so you get a lot of phenomena that you would not get with light. And in fact, nonlinear optics, which in the past was possible only with lasers at very high fields, can be achieved with atoms with very low fields. You can get such things as four-wave mixing with atoms. You can get Bragg interference of different atomic beams. This whole world of atomic phenomena has been opened up to this world of laser beams. And so the thought of light being rather unique in its coherence properties, for instance, is no longer valid. You can get coherence in large atomic systems, and these coherences are being exploited in quite novel ways. If you have coherence in systems which can interact with each other, you have the elements that you need for quantum computation. You have nonlinear elements. You can make switches. You can have one atom talk to another. You can have one atom trigger one photon. This whole new area of atom optics, in which you're involving not just the optics of atomic beams and light beams, but the two of them together, is enabling the creation of new quantum devices and new states of matter. This development of nonlinear atom optics occupied many groups for quite a while, but the field has now moved on beyond that. Methods for developing fermionic degenerate systems have now been developed. It's an outgrowth of the techniques for making Bose-Einstein condensates. In Bose-Einstein condensates, the atoms have bosonic properties. Namely, they have an even number of half spins. If you have atoms with odd numbers of half spins, they will be Fermi statistics, which is totally different. And it turns out the physics of the fermionic atoms is much richer than for the bosonic atoms. So this is the chief heritage, I think, of the search for Bose-Einstein condensation, is that it's opened the way to the study of what we call Fermi degenerate systems. Now, in a Bose condensate, all the atoms are in the lowest state. In a Fermi system, you can only have one atom in a state, so they're entirely different. The atoms pile up, one in each state. But we've learned how to make those systems now, and they're a very rich system. They're a very rich system because they represent fermionic, strongly correlated systems, of which the most common one that we know is the electron gas in matter, in metals. With fermionic gases, you can also cause this pairing and form superconducting atomic systems. I mean, this is something which no one ever dreamt of when this whole field opened. And now there is a lot of energy in trying to understand the physics of superconducting systems. The physics of superconducting systems is not well understood. High temperature superconductivity, for instance, is now is still a baffle years after it was discovered, when everyone thought the theoretical problem would be solved within a reasonable time. It's still an unsolved problem. And there are many other problems in electron behavior in matter which are unsolved. It turns out with these fermionic atomic systems, one can study these problems in a form never before possible. For one thing, you have total control over the system. It's possible to control the interactions between these atoms. You can make them attractive or repulsive or zero. Another thing is that you can study them in exquisite detail. You can take these systems and actually look at them in real time. You can take photographs of them and see how they behave. You can see phase transitions while they're taking place. You can see ferromagnetism and antiferromagnetism and other states which we know exist in matter, but you really can't study and you can't manipulate. So this whole new world of fermionic systems has been opened and is being pursued right now. That Hamiltonians, which condensed matter theorists provide to describe the behavior of systems, can now be studied in great detail, because you don't need to take matter as nature gives it to you. We can create it ourselves in the laboratory and manipulate it and control the parameters. We can control the interactions, the densities, the geometries of the system in ways which are never before possible. So this is all an outgrowth of the discovery of Bose-Einstein condensation. And although the atom laser seemed very controversial when the term was first used, I think the community has come around now, and essentially everyone agrees, yes, you can create atoms in an atom laser, and it's a proper laser, just like light in the light from an ordinary laser. But there's much more to this area of ultracold atoms than that. The idea of a quantum computer was put forth many years ago by the great physicist Feynman, who pointed out that if you could make such a device, a quantum computer, you could simulate the behavior of quantum systems which you couldn't possibly compute otherwise. So this theme of quantum simulation is sort of the underlying theme of the current quest for quantum computers. Well, the current theme of this field right now is quantum simulations, of building systems under such control that we can look at their behavior of known Hamiltonians and study the behavior of those Hamiltonians using the atomic system to simulate any other system which is governed by this Hamiltonian. There's great expectations that these simulations are going to totally change the way we understand matter. So this is a wonderful example of how physics leads from one area to another, and that ideas which seem totally absurd can come true.